Welcome to this course Applied Thermodynamics Internal Combustion Engine Module 3. So, here are the list of topics. We are now in the lecture number 4, that is thermodynamic analysis of air standard cycles. So, in this lecture we are going to discuss about three important cycles. One is Otto cycle, which is an ideal cycle for SI engines, diesel cycle, which is an ideal cycle for CI engines, dual cycle, which is a combination of both Otto and diesel cycle as far as the combustion mechanism is concerned. So, let me give you some brief introduction about what the air standard cycle means. Ideally, when you look at Carnot cycle, we need a working fluid to run the engines. In a similar sense, when you discuss about SI engine or CI engines, there are working fluids which are very specific to those engines. For example, in SI engines, petrol is the base working fluid. For CI engines, diesel is the base working fluids. But before you go to those analysis, the first estimate that one should know that the first estimate one should know about the fact that they should give some estimate as far as thermodynamics analysis is concerned. To simplify this analysis, the base working fluids, like that is petrol or diesel, they are replaced with air. So, when we are replacing the air, working fluid with air, there are certain assumptions that we are going to make. So, to study all these things, the importance of air standard cycles is realized. So, whatever I have explained, that the cyclic process in IC engines is very complex, either it is a 4-stroke or 2-stroke. The intake charge, that is air in CI engine, and premixed fuel air mixture for SI engine is injected and mixed with the residual exhaust of the previous cycles, since it is a cyclic process. After the compression and combustion, the intake charge turns into the exhaust product, which is largely in the form of CO2, H2O, N2 and other residues. Hence, the real process involves charges with changing composition, and these open cycles are difficult to analyze. So, to simplify this analysis, a manageable option is to consider air standard cycles with certain assumptions. So, based on this approach, the air standard cycle is considered as the thermodynamic analysis for CI and SI engines. So, for SI engines it is the Otto cycle, for CI engine it is the diesel cycle, and there is another cycle which is also gives a good estimate when you combine the combustion process of Otto and diesel cycles in a dual cycle. So, we will discuss it one by one. So, before you discuss them, let us see that what are the assumptions involved. So, when you tell that we are going to replace with air as working fluid, there are certain logics, means that why we should go for air as a working fluid. So, it has been seen that when you see actually the charge, fresh charge, which is a mixture of fuel and air, the major constituents is air, because roughly the ratio between air and fuel is about 15. So, that means 15 times by mass of air is used to prepare the fresh charge involving fuel and air. So, predominantly the contents are air. Second thing is that the real open cycle, in the IC engines it is a real open cycle, and it is because the fresh charge is inducted every time, but in our assumption of air standard cycle it is assumed that the combustion products are exhausted to atmosphere and they are fed back with the charge, fresh charge in the intake systems. So, in one way that combustion product goes out, side by side we are feeding the fresh charge. Third assumption is that since the combustion is not possible with air alone, so it is equivalent to consider the thermodynamic heat addition process appropriately, means that physically the cycle requires the heat addition processes through fuel, but here it is not possible to consider that. Rather we say that whatever the amount of heat that is required, they are being fed into the cycle. Next assumption is that the exhaust process carries a lot of enthalpy out of the system, so that the closing system closing process can be considered as a heat rejection process. Moreover, the actual engine processes are approximated as near optimal to ideal thermodynamic processes. Now, we will consider about the assumptions that are involved in our calculations. That is number 1. Number 2 is that we also have to give a thermodynamic meaning about the processes that are encountered in the IC engine. So, first assumption in that line is that the intake and exhaust strokes are constant pressure processes. Compression and expansion strokes are isentropic processes. Combustion process can be idealized either by a constant volume processes which is used in SI engine cycle, or a constant pressure processes which is used in the CI engine cycle. This exhaust blow down process is treated as a constant volume process, and for all the study working fluid is treated as air and it is considered as a ideal gas. So, here I have written down some basic equations that an ideal gas equation of state follows. First thing, small PV, pressure into specific volume, is equal to RT, P capital B is equal to MRT. So, that P becomes rho RT, enthalpy can be represented as Cp times T, and internal energy can be replaced as Cv by T, and specific ratio is written as K is equal to Cp by Cv. So, ideally for air, these Cp and Cv values are treated as 1.005 kilojoule per kg Kelvin, that is for Cp, 0.718 kilojoule per kg Kelvin, that is for Cv, and R nothing but Cp minus Cv 0.287 kilojoule per kg Kelvin. And here we consider the specific heat ratio as 1.4, but to bring more clarity or more closeness to our analysis, we are going to use the Cp value in terms of combustion products, where they are slightly different. That is, we are going to use the value of K as 1.35 and corresponding Cp and Cv values of combustion products in our analysis. But interestingly, you can see that R value Cp minus Cv for air as well as combustion products, they match very well. So, in some sense where R is considered, it whether you take combustion product or air, this remains same in the calculations where R is involved. So, with this logics, it makes some sense that air can be considered as working fluid in air standard cycles for SI engines, CI engines and dual cycles. So, let us start with the first cycle, that is Otto cycle. The air standard model for a 4-stroke SI engines is considered for Otto cycle. So, it starts with an intake stroke. As you see in this figure, there are two types of diagram which is represented. One is pressure volume diagram, other is temperature entropy diagram. So, you start with the process 6-1, which is we call as a intake stroke. So, it starts with piston at TDC. So, it is a constant pressure process, as you can see from atmospheric air at atmospheric condition is getting into this cylinder. So, it is a intake stroke, that is from 6 to 1. But ideally the inlet process is slightly lower than atmospheric, so that flow can enter, because we need a pressure differential. So, at that time when we are in the state 1, the temperature of air increases as the air passes through hot manifold. So, normally whatever atmosphere temperature we are consider, that is slightly higher, because when it passes through the intake manifold, its temperature of air increases and close to 25 to 35 degrees centigrades higher than the atmospherics. So, that means normally at state point 1 is higher than atmospheric. Then we have compression stroke. So, the compression stroke starts when the piston moves from BDC to TDC. So, in this diagram we can see that when the piston moves from BDC to TDC, this process 1 2 happens. So, and this process is isentropic in nature, as you can see in the TS diagram. So, in the beginning of the compression stroke, the intake valve is not fully closed, but and at the end of the compression is affected by spark plug firing. So, normally after the compression stroke, you need to start the combustion. So, spark plug needs to be fired somewhere close to 0.2. So, although we see a very sharp rise, but ideally it is not so. So, but in our air standard assumption, that consideration is not taken seriously. So, now in the summary is that in the compression stroke, the both pressure and temperature increases. Next is the heat addition process. So, we have already explained that heat addition in a SI engine process can be best approximated when it is considered as a constant volume processes. So, that means point 2 to 3 we can regard it as a constant volume processes when the piston is exactly at TDC, but in reality you will find that the combustion starts slightly before TDC and it reaches maximum speed at TDC and then terminates little after TDC. So, somewhere in this zone we can see, in reality you will find that the sharp peak what you are seeing in the Otto cycle is not so, but the air standard cycle assumption does not take into account of these facts. So, the energy added in the air rises the peak pressure and temperature at point 3. Then we have power strokes. So, after the combustion process is over, so pressure and temperature gets increased. So, the piston face sees a force acting on this acting on it. So, in this process the piston starts moving from again from TDC to BDC. So, we call it as a power strokes, but in real engines the power stroke is affected by last part for the combustion processes, because till that point of time the combustion is not complete, but the power stroke has also started. And also this power stroke is also affected by the opening of exhaust valve, that is before BDC. Now, in the process of this expansion we can see 3 to 4 is an isentropic process, and in this process of expansion the pressure and temperature decreases as the volume increases from TDC to BDC. Then we have heat rejection process. So, that is regarded as a constant volume processes from 4 to 1, and this happens close to BDC or at BDC, mostly at BDC, and this 4 to 1 is represented in the temperature entropy diagram like this. So, it is a constant volume process. Then the last stroke which we call as a exhaust stroke, that is from 5 to 6. So, in a real engine the exhaust product goes out, that means when the piston is at BDC the exhaust blow down starts, the exhaust valve opens. So, then because of this reason, the end of exhaust stroke, the engine experiences 2 revolutions of crankshaft. That means, piston is back to TDC to begin a new cycle, closing the exhaust valve and opening the intake valve. So, this happens at the end of exhaust stroke, and as you can see from this pressure volume diagram. So, when we started the intake stroke, it goes as 6:1, and when you come as exhaust stroke, it goes as 5:6. Hypothetically or ideally, the 5 and 1 points are close to each other, are very close. So, in our air standard cycle, this point state conditions at this point 5 and 1 are almost same. So, when you do the work calculation, since it is a constant straight line and arrow for each straight line are opposite in nature, see the work in that PV diagram will get cancelled. So, that means the intake and exhaust stroke work does not come into the thermodynamic analysis of Otto cycle. So, we will see this one by one. Now after explaining all these thermodynamic process, let us see that how we can represent them in the form of equations. So, first thing is that when you look at the cycles, we basically look at the compression ratio, because of the piston location between 1 and 2, that is between BDC and TDC. So, we represent the compression ratio as RC, which is nothing but V1 by V2. That is one important parameter which we are going to use. Now, let us see the process wise. So, let us start with the intake process, that is 6:1. So, it is a constant pressure process, P1 is equal to P6, and that is nothing but P naught here. And the work for this process, we say it is a work, specific work for the process 6:1, we can write is P0 times into V1 PV work, we can write P0 times V1 minus V6. Similarly, for process 5:6, another expression can be written where P5 is equal to P6 is equal to P naught. So, that W56 becomes P0 into V6 minus V5. So, if you add this equation, work transfer for 6:1 and 5:6, it will be 0, because they will cancel each other. Then we move to the compression process, that is for 1 to 2. So, we can write the equation as isentropic process. So, isentropic equation can be used for state points between 1 and 2. We can write the temperature equations, and there we will find a ratio V1 by V2. We define it as a ratio of compression ratio. This V1 by V2 ratio becomes RC. Similarly, we can write pressure in terms of compression ratio. Then for this, since it is an isentropic process, so Q12 will be 0 and W12 will be CV times T1 minus T2. Then for process 2 to 3, that is constant volume heat additions. So, V3 is equal to V2 is equal to VBDC. So, in that process there is no work, Q23 is 0, small q23 nothing but Q in, that is the assumption that we are replacing the at a Q in, that is nothing but CV times T3 minus T2. So, in that process when we have the maximum pressure in the cycle, that is T3 nothing but T max. In fact, maximum temperature of the cycle also T3 and maximum pressure is P3, and that is nothing but we denote it as a maximum pressure in the cycle as P max and T max. Now, in this situation we are trying to replace or trying to make some correlation that how we can make this Q in calculations in our analysis. So, ideally instead of representing this small q to 3 where there is no mass term is involved. So, but in to some extent in reality the fuel takes a role. So, in that sense what we can say is the Q in, that is heat input that comes in the process 2 3 can be represented as mass of the fuel and into Q, that is calorific heating value of the fuel, and multiplied by the combustion efficiency. When we multiply these three things, we get the total Q in, not in terms of kg. So, we get a total Q in, that is nothing but mm, that means total mass, that is mass of the fuel and mass of the air, into Cv, that is a constant volume process. So, and temperature difference T3 minus T2. So, these two equation gives rise to another equation, important equations, that is QCV into combustion efficiency is equal to AF. AF is nothing but air fuel ratio plus 1 into Cv into T3 minus T2. So, this particular equations is very vital in calculating in bringing the air fuel concept into the thermodynamic calculation of Otto cycles. So, rest of the things are similar to what we have already discussed, that is process 3-4, that is expansion process, which is almost opposite to that of compression process. So, we can write similar isentropic equations for expansion process. Process 4-5 is a constant volume process because it is a blow down process. So, that point of time V5, V4 and V1 all are equal, which is nothing but VBDC, and in that process W45 will be 0, Q45 also becomes for the process 4-5. So, it can write as Cv times T1 minus T4. So, from this also we can find out the total heat. So, instead of calculating heat per unit per kg, we can calculate the total heat as Q out, that is bringing total mass into picture. So, from all this analysis we can calculate the net work, which is nothing but difference in the expansion work and compression work, and Q in, which is heat being supplied by the fuel from these equations. Then we can find out the thermal efficiency of the Otto cycle as W net by Q in, and ultimately when you bring out these isentropic relations, final expression we can represent this Otto cycle thermal efficiency as eta T is equal to 1 minus 1 by RC to the power k minus 1. It is a simple expression, but what we can see that RC is a compression ratio. That means indicated thermal efficiency is a function of compression ratio. When you plot this equation, it shows a rise. That means with when you increase the compression ratio, the efficiency rises. So, it can be plotted in the range of compression ratio in each engines are operated. The another model for air standard model for 4-stroke CI engine is a diesel cycle. So, here I am not going to explain them in the details, same processes are involved, that is except the certain change that I will explain. The first one, intake stroke process 6-1, compression stroke process 1-2, heat addition process, that is process 2-3. Here it is the change, because here it is a constant pressure processes when both the valves are closed. Then you have power stroke or expansion stroke, heat rejection process and exhaust process. But some important analysis here we are going to make here, that the assumption of constant pressure process because is more relevant here, mainly because fuel is added into the air. So, it is not possible to maintain the constant volume process when fuel is added. So, best approximation is that we should go for a constant pressure process. Since the fuel is continuously injected towards the end of compression stroke, and we can define a ratio which is called as fuel cutoff ratio, that is based on the what time the fuel injection starts and what time the fuel injection stops. So, this is the at 2 it starts and at 3 it stops. So, based on the ratio V 3 by V 2, a fuel cutoff ratio can be defined. So, rest of the processes are simple, and now we will revisit the thermodynamic analysis. So, here we can see that all equations follow the similar one as we do in the Otto cycle, but only difference that we can see in the heat addition process, that is between Q 2 3, while calculating the heat input we are using Cp here. Instead of Cv we have to use Cp here, and since it is a heat addition process, that will also and since it is a constant pressure process, it also incurs the work transfer WT3, and also we define a parameter fuel cutoff ratio, that is beta, which is nothing but V3 by V2. And from this analysis we can V3 by V2 can be replaced with T3 by T2. But ideally, when we are bringing the calorific value and combustion efficiency of the fuel, then instead of calculating the specific values of Q, we can represent it in the total value, that is total Q in, and that can be represented by bringing the fuel calorific value, mass flow rate of the fuel and combustion efficiency. So, based on this equation we can frame this particular equation, which is QCV into combustion efficiency is equal to AF plus 1 whole bracket Cp and temperature difference between T3 and T2. Rest of the things, process 3-4 is a expansion process, and expansion process is isentropic in nature, that you can have it. You can use the corresponding equation. Process 4-5 is your exhaust blow down. So, you can, it is a constant volume processes where we have work transfer as well as where we have heat transfer equations are involved. So, from this one can calculate the thermal efficiency, which is nothing but ratio of W net by Q in. As you can see, the efficiency calculation apart from this particular ratio as we see in the Otto cycle, there is another term that gets added, and this particular term involves the fuel cutoff ratio beta and the specific heat ratio for the combustion products. When we are going to plot the thermal efficiency versus fuel cutoff ratio for different compression ratio, we can plot it. So, as you can see, when the compression ratio increases, the thermal efficiency increases. When the fuel cutoff ratio increases, the thermal efficiency drops. So, this is the some summary is that when you do this diesel cycle analysis, the we require the compression ratio and fuel cutoff ratio to calculate the diesel cycle efficiency. Thermal efficiency increases with compression ratio and decreases with increase in the fuel cutoff ratio. For a given CR, compression ratio, indicated thermal efficiency of Otto cycle is higher than the diesel cycle. The constant volume combustion, and thus the constant volume of combustion at TDC is more efficient than the constant pressure combustion process. CI engines operate with higher compression ratio as compared to SI engines. So, thus they have higher thermal efficiency, because now in general the CI engines operate higher compression ratio, because of this reason they have higher thermal efficiency. Then we will move on to another cycle, which is dual cycles. So, people think of that how we can improve the efficiency of Otto cycle, at the same time we can approach the efficiency of diesel cycle just by doing some alteration in the heat addition process. So, the alteration, by doing so what we can say is that instead of having constant volume processes where there is no work output, and if you replace with a constant pressure process, then that means there can be certain work output. So, in that process we will get your work output increases, and thereby you can enhance the cycle efficiency of Otto cycle closer to diesel. So, in those with those concepts, the modern high speed engines accomplish dual mode of combustion process, first by a constant volume, then it is followed by a constant pressure process. So, in this case the fuel injection starts earlier in the cycle, that means 20° before TDC, so that first fuel ignites late in the compression stroke as that of Otto cycle, followed by the diesel cycle. So, the peak pressure remains high into the expansion stroke due to finite time required to inject the fuel, and last part of the fuel is injected at TDC, so that combustion of the fuel keeps the pressure high in the expansion stroke. That means, when the expansion stroke starts, this combustion keeps the expansion pressure high. So, we will have a larger domain of expansion stroke. So, this particular concept of combustion process is known as dual cycle, or people call it as a limited pressure cycle. Many a times it is also referred as modified Otto cycles with limited upper pressure. So, as you can see in this figure, that in a dual cycle the change that happens is heat addition process, first from 2 to x, that is at a constant volume process, and from x to 3, that is at constant pressure process. So, here corresponding temperature diagrams also drawn for the similar concepts. Now, this heat addition process does with all the valves closed, and we call this as a combustion part 1, combustion part 2, that means combustion takes place in the two parts. So, this here also the analysis remains simple. I do not want to go deep into this, and here what we can see is that the change that happens is work transfer, that is between process x 3 and process 2 x. So, these are the two processes that is going to alter. So, here you can see this for process x 3 there is heat transfer and also there is work transfer. Process 2 3 there is only heat transfer, but there is no work transfer. So, in that process we get an additional work output through same amount of heat being supplied in two modes. So, thereby we can calculate the thermal efficiency as a function of three factors. First one is the compression ratio, other one is the fuel cutoff ratio, that is from V3 to V2, and there is also a parameter alpha, which is nothing but the pressure ratio. This pressure ratio one can define by this particular concept, that is alpha is defined by Px by P2, that is nothing but P3 by P2, and we can write it as a Tx by T2, and finally the same alpha you can represent in the form of compression ratio and P3 by P1, that is maximum pressure, peak pressure to the minimum pressure, maximum pressure P3, minimum pressure P1. So, this alpha is explained here, and from this calculation what you can see, this has two parts, one is Otto cycle efficiency, other is this additional part involving alpha, beta and k. So, whatever I have explained, this is shown here, that the one is the fuel cutoff ratio, other is the pressure ratio that takes part into the calculation of thermodynamic cycle efficiency. The air standard cycle of CI engines is obtained through diesel cycle is higher than that of Otto cycle, but here you must remember that diesel cycle operate at higher compression ratio, whereas Otto cycles operate at lower compression ratio. So, this is the reality. The real engine has less indicated thermal efficiency with respect to its air standard efficiency of corresponding cycle. So, it is mainly because of the fact that changing composition, heat losses, valve overlap, finite time required for cycle process. So, all these things will come back later point of this lecture or module, and but at this stage we can say that when you see an actual cycle operating in a diesel cycle, its efficiency is about, we can roughly say it is about 85% that of diesel cycle. For example, if you calculate the cycle efficiency of a diesel cycle and take a actual number, why actual number? Because of this consideration, changing composition, heat losses, valve overlap, finite time. So, the actual efficiency will be less than that, which is roughly we can say about 85% of the corresponding diesel cycle. Now, next approach is to compare the air standard cycles. One way of comparing them is that for same inlet conditions and same compression ratio. So, we have pressure volume diagrams and temperature entropy diagrams. So, what we are making constant is for same inlet conditions. So, the condition 1 is same for all the cycles, and also compression ratio is same, that means point 1 and 2 locations are same. So, by doing so what we are going to see. So, as you can see here that for same condition 1 and 2 compression ratio and same inlet conditions, if first I need to draw an Otto cycle. So, when I draw an Otto cycle for same compression ratio, the Otto cycle is represented as 1, 2, 3a and 4. Now, with same compression ratio, if I want to draw the diesel cycle, then what should I do? Then from point 2 I have to draw a constant pressure line. So, it is intersects the expansion curve 3a and 4 at 3c. So, this represents the starting point of the heat addition for diesel cycle point 2 and heat addition stops at point 3c. So, 2-3 process heat addition process, and somewhere down the line if you want to represent a dual cycle, we can cut off at any point on the line 2, 3a. So, here it is represented as x. So, the dual cycle is 1, 2, x, 3b, 4, 1. So, in similar sense we can also represent the temperature entropy diagrams. Now, when we are actually comparing the thermal efficiency, we can represent is eta T is equal to 1 minus Q out by Q in. So, as you can see for each cycle the heat rejection is same, that means Q out is same, but heat input is different. So, heat input is different, why? Because we can get it from the Otto cycle, we can get it from the temperature entropy curve, and we can see for Otto cycle it is the highest, because the area under the diagram of for Otto cycle is the highest. So, that is nothing but the cycle 1, 2, 3a, 4. So, by putting this logic or concept, we can say the thermal efficiency of Otto cycle is highest. The another way of comparison is that based on the same inlet condition and same peak pressure and temperature. What does this mean? Is that normally the engines are operated in different compression ratio. So, the realistic approach for them is to consider the Otto, diesel and dual cycles for same inlet conditions and same peak pressure and temperature. In doing so, what we are going to do is that same logic we can first say that we have to consider same inlet condition and same peak pressure. So, peak pressure remaining the same. So, obviously, it will be a diesel cycle first. So, you can first draw a diesel cycle, that is 1, 2C, 3, 4, and from this diesel cycle we can derive the Otto cycle as 1, 2A, 3, 4 by maintaining same peak pressure and same inlet conditions, and somewhere we have to make a cutoff to draw the dual cycle, that is 1, 2B, X, 3, 4 and then 1. So, in same sense we can also calculate the heat addition in the diesel cycle is the highest, that is Q in is highest for this particular cycle. So, based on that equation we can find for these particular conditions, that means a different compression ratio, but same inlet condition and peak pressure, diesel cycle is the most efficient one. So, with this we conclude the end of the lecture. Now, let us solve some numerical problems based on the study what we have done so far. So, the first problem which I am going to discuss to consider a 4 cylinder 2.5 liter SI engines with compression ratio 8.6 and it operates on Otto cycle. So, basically this is an Otto cycle analysis. So, we have to use all thermodynamic equations of Otto cycles. So, the fresh charge is condition which is at the inlet condition is 100 kilopascal and 60 degree centigrades. We also have given with air fuel ratio of 15 and the fuel calorific value of 44 megajoule per kg with combustion efficiency of 97%. So, we are asked to carry out the complete thermodynamic analysis. So, first thing to start this problem, let us take that what Cp, Cv and gamma or K value we should take. So, beginning analysis we have represented the Cp value as 1.108 kilojoule per kg Kelvin, Cv we can treat it as 0.821 kilojoule per kg Kelvin and K as 1.35. So, this is in contrast with air, because air has this number relatively different, and why we are going to use this, these are values used for combustion products, and with this value if you do the analysis we will get a number which is close to the actual cycle. So, to start the problem, first thing we need to find out the state points, or for all the state point we have to find out the pressure, temperature and volume. So, for the volume calculations we have to start with the VDC and TDC. From the data we can give the displacement volume Vd is 2.5 by 4, that is 4 cylinder, this is about 0.625 liter. So, we can represent in meter cube 0.000625 meter cube. So, we know the compression ratio RC as 8.6, that is nothing but Vd plus Vc by Vc. So, this will give you the Vc as 0.0040822 meter cube. So, we have Vc and we have Vd. So, we can find out V1, that is Vd plus Vc. This number is 0.000707 meter cube. So, state point 1 is known. For state point 1 pressure is given 100 kilopascal, temperature is given at 60 degree centigrades. So, equation of state can be used to find out total mass, that is P B by R T. So, R is 287 and pressure known, volume known. So we can find this M mass is 0.00074. So this mass is total mass, that is involving MF plus MA. So we have given with air fuel ratio as 15. So from this we can find out MA as 15 by 16 into mm, and that number is 0.00069 kg, and MF will be 1 by 16, that number mm, that number is 0.00005 kg. So these are the data we need to calculate. Then after that your cycle analysis will be simple. So for state 2, compression process, P2 would be P1 into RC to the power K, that number becomes 1826 kPa. T2 becomes T1 RC to the power K minus 1, that number is 707 K. Then for process 3, state 3, we can use the heat input equation. So here we are using MF, that is Q in is equal to MF Q CV calorific value into combustion efficiency is equal to mm total mass into CV times T3 minus T2. So in this equation all the data is given. Your calorific value is QCV 44 megajoule per kg, CV already I have written this data. So this equation will give you combustion efficiency is 97%. So this will lead to the value of highest temperature T3 as 3915 Kelvin. Once we have T3, we also know V3, because V3 is equal to V2, and from that P3 we can calculate as P2 into T3 by T2, that is equal to 10111 kPa. Okay, so we are able to get the state point 3. Then we are left with state point 4 and efficiency calculations. So for state 4, we can write T4 is equal to T3 into 1 by RC to the power K minus 1, that number will be 1844 K. P4, and this process is isentropic. So I am using this isentropic equations. P4 is equal to P3 into 1 by RC to the power K. So this is 554 kilopascal, and V4 we can find out mRT4 by P4. So mass already known, total mass mm. So this number will be 0.000707 meter cube. So with this we calculated all the state points, properties values at all the state points. Now, we have to revisit work and heat calculations. So, first thing W34, that is work involved here, is m r T3 minus T4 divided by 1 k minus 1, and W 12 would be m r T2 minus T1 divided by k minus 1. So, this is the compression work W12, that is 0.227 kilojoule, and this is W34 is your expansion work, that is 1.257 kilojoule. Then Q in, that is MF into QCV into combustion efficiency, that is 2.134 kilojoule. When you put this value, you will get these numbers. In the end, thermal efficiency, we can write W net by Q in. So, these two terms will give you W net, that is difference between these two values, and this is your Q in. So, this ratio turns out to be 1.03 divided by 2.134, and that is about 48%. Okay. This is all about the thermodynamic analysis of an SI engine. And in the similar logic, we have another problem, that is 4-cylinder 4-liter truck engine that operates in a dual cycle. Here the air fuel ratio is given, air fuel ratio is 18, compression ratio is 16, and in bore diameter is 100 mm. Intake condition is 100 kilopascal and 60 degree centigrades, but the entire idea is that heat addition process. So, total heat addition process is divided into two halves. So, the first half is at constant volume and second half is at constant pressure, and both amount is equal. So, we need to calculate the pressure, temperature and at each states. So, the solution of the problem, we can start with similar way as we did it. So, displacement volume becomes 4 liter by 4 cylinder, that is 1 liter, and this number is 0.001 meter cube. From Earth's compression ratio, that is 16, this will give you the clearance volume as 0.00040,667 meter cube. So, V1 becomes Vd plus Vc. P1 is given 100 kilopascal, T1 is 60 degree centigrade. So, these two equations will give you the total mass of fuel, that is Pv by RT. As we mentioned, Cp, Cv and K, we have to use the same value as we have written in the lecture material. K is 1.35, Cv is 0.821 kilojoule per kg Kelvin, this is 1.108 kilojoule per kg Kelvin. So, this mm we can get 0.00112. Then we have air fuel ratio as 18, then we can get MF as 0.40. 578 kg. Okay. Now from this compression process state 2, we get T2 as 879 Kelvin, P2, that is isentropic compression process 1 2, we get the number as 4222. Then heat addition. So Q in can be calculated as MF QCV into combustion efficiency, that number will be 2.46 kilojoule. Now here this Q in has two parts, one is Q2x and Q3x3, and they are half, so it is 1.23 each. Then from this 2x, that is CV times Tx minus T2. So from this equation we can get Tx as 2217 Kelvin. Px becomes mRTx by Bx. So this will be 10650 kilopascal. Then from this Qx3 equation, that is Cp times T3 minus Tx, we can get T3 as 3208 Kelvin. From this we can get P3 as mRT3 mm by P3. So this is 0.00097 meter cube. So for state 4, the idea is that V4 will be V1 and that is known 0.0010667 meter cube. Then we can find out T4 as T3 into V3 by V1 to the power k minus 1, that is 1386 kilopascal. P4 also can be calculated as P3 into V3 by V4 by to the power k, Pv to the power gamma. Okay. So this number is 418 kilopascal. So we have P4 and T4. Then exhaust state 5, that is T5 is equal to T4 into P5 by P4 to the power k minus 1 by k. So this number will be T5 would be 957 Kelvin. That means exhaust temperature at point 5 would be 957 Kelvin. So this is all about the thermodynamic state, pressure and temperature of the cycle. So we are now and also we calculated the exhaust temperature. So here now main job is to calculate indicated thermal efficiency. So here we require W net. W net has three parts, one is Wx3 plus W34 and minus W12. That W12 is your compression part and this is your expansion work. So, for each stage this Wx3 is nothing but P into V3 minus Vx, W34 is M R T4 minus T3 divided by 1 minus K, W12 would be M R T1 minus T2 divided by 1 minus K. So, when you calculate using this, you will have W net would be 1.495 kilojoule. So, earlier we calculated Q in mm QCV into combustion efficiency. So, there is no data of QCV. So, for the time being we can use QCV as 42.5 megajoule per kg is for the fuel which we are going to use, and combustion efficiency as 97%. So, this will give you the value of Q in as 2.46 kilojoule. So, efficiency would be W net by Q in, and this is 60.7%. So, the analysis is very lengthy, but we have to, due to time constraints, I have explained it very briefly. I hope you can understand this problem, and for all these equations you can refer the slides in which these equations are given elaborately. So, with this I conclude this talk for today. Thank you for your attention.